want to know everything about optical properties? Are you in Dr. Yusha's 3015 class? Do you want extra points to stop yourself from taking the final? Well then, you should have made this video. In this video, we're going to be deriving the Fresnel's equations, which describe how light moves through materials with different refractive indexes. But first, we'll be deriving Snell's law, which will help us simplify the equations later on.
Ibn Sahl discovered the law of refraction in 894 AD in Baghdad and used it to create lenses that eliminated spherical aberrations. These anaclastic lenses are still used today to help with astigmatism. Willebord Snellius rediscovered the law of refraction in 1621 in the Netherlands, and only several centuries later was it found out that Ibn Sahl had been the first to discover the law. The name of the law has not been changed and currently reflects Willebord Snellius' discovery.
At first I was afraid, what could the answer be? It said, given this position, find velocity. So I tried to work it out, but I knew that I was wrong. I struggled, I cried, a problem shouldn't take this long. I tried to think, control my nerve. It's evident that speed's tangential to that time position curve. This problem would be mine if I just knew that tangent line, but what to do? Show me a sign. So I thought back to calculus, way back to Newton and to Leibniz and to problems just like this. And just like that, when I had given up all hope, I said nope. There's just one way to find that slope, and so now I will derive, find the derivative of x position with respect to time. It's as easy as can be, just have to take dx dt. I will derive, hey, hey.
From this, you can easily put Snell's law into the form that it's commonly seen in, n1 sine theta 1 equals n2 sine theta 2. This image shows the effect of Snell's law on waveforms. One can easily plot the sine of incident or refractive angle given one angle and the ratio of refractive indices for any two given materials, which serves as the slope for this linear relationship. Snell's law shows that incident and refractive angles have their limitations. The largest incident angle at which any light will be refracted is called the critical angle, which can be calculated by the inverse sine of n2 over n1. In this case shown, the refractive index of the water would be n1, and the air's refractive index would be n2.
Why is my reflection someone I don't know?
Any incident angle larger than this critical angle would result in total internal reflection, in which all the light is reflected off the boundary and stays within the first material.
Augustin Jean Fresnel began research in optics around 1814. Fresnel equations describe how light behaves as it moves through media with one refractive index, n1, to a different refractive index, n2. Both reflection and refraction of the light may occur.
Snell's law must be used to find the angle that the transmitted wave will propagate at. That's the theta t you see in equation 1, where n1 and n2 are the refractive indices of the different materials that the wave is propagating through. For equations 2 and 3, you have the parallel conditions of the electric and magnetic fields. In parallel polarization, the electric field vector is inside the plane of incidence. Equation 2 is the boundary condition for the electric field, and the boundary condition for the magnetic field is equation 3. Equation 4 is the relation for the electric and magnetic field amplitudes for the wave, which is found via Maxwell's equations. We accompany this with the definition of a refractive index, and applying this definition yields equations 5 and 6. For equation 6, we accompany this with the understanding that most materials with optical properties are non-magnetic, and therefore the magnetic permeability of both materials is approximately equal to the permeability constant. The Fresnel equations for the parallel polarized wave can be found through the definitions of the amplitude, reflection, and transmission coefficients, which are given in equation 7. The Fresnel equations are there for equations 8 and 9. For the perpendicular polarized wave, we need the boundary conditions for the electric field and the magnetic field, presented here as equations 10 and 11. We're also going to use the same definitions for amplitude, reflection, and transmission coefficients. Therefore, the Fresnel equations for the parallel polarized wave for amplitude, reflection, and transmission can be found as the 12th and 13th equations. Now, these four equations we've derived here are fairly nasty, so what we can do is simplify them a little. To do this, we're going to use Snell's law and put the equations totally in terms of one material or another. We're also going to accompany these with the trigonometric identities, which give us our final equations. These equations describe the behavior of light as it moves between materials with different refractive indices.
Hey guys, I finished the trigger and stuff.
You know, we're not using that, right?
You couldn't have told me that earlier?
I know